Hello, everyone. Welcome to Palladium Magazine's Digital Salon with Stephen Wolfram. I'm Wolf Tivy, editor-in-chief of Palladium. I'm joined by Ash Milton, managing editor.
Hey, everybody.
Our guest today is Dr. Stephen Wolfram. He is the creator of Mathematica, Wolfram Alpha, and the Wolfram Language, the author of A New Kind of Science, the originator of the Wolfram Physics Project, and the founder and CEO of Wolfram Research. Over the course of more than 4 decades, he has been a pioneer in the development and application of computational thinking, and has been responsible for many discoveries, inventions, and innovations in science, technology, and business. Welcome to the salon, Dr. Wolfram.
Pleased to be here.
Great. So we're joined by our live audience of Palladium members and friends. The conversation will be recorded and rebroadcast on YouTube and as a podcast. To become a Palladium member and get invited to upcoming salons, please visit palladiummag.com/subscribe. The plan is for Ash, Stephen, and myself to have a discussion for about 45 minutes and then move to questions from the live audience. So please be sure to use the Q&A function in Zoom to post your questions and upvote other people's questions. To get started, I want to put a little bit of a framing on our discussion. So our interest is in the institutional, sociological, and epistemological dimensions of Stephen's work. The big question guiding this discussion is therefore how, as a society, we can do better science and how to think about these things better, especially with focus on the human structures. So let's get into the first question. So Stephen, you've now formally launched your Wolfram Physics Project, applying the computational paradigm you laid out in A New Kind of Science to fundamental physics. This is very different from the established, let's call it mathematical analytic paradigm. What kind of questions do you think this new paradigm can answer in fundamental physics? How does it help us?
Well, the basic question is, how does our universe work? And the thing we're trying to do is to find what the fundamental rules for the universe are. Mm-hmm. It's not been clear that there would even be fundamental rules for the universe. People imagined that back in antiquity. Mm-hmm. People kind of, when sort of mathematical science started to be done in the 1600s, there was sort of a new hope that there might be kind of a way to understand the whole universe. And there have been a series of times when people have sort of thought, we're almost there. We've almost got a kind of formal way to understand our whole universe. But so far it hasn't worked. And from the things that I've studied about sort of the nature of computation, I kind of got to suspect about 30 years ago, maybe there is a way to have even a quite simple rule from which we can basically generate or grow the universe. And so I tried doing various things, and I actually got kind of put off by the fact that my friends, the physicists, and I used to be one of them, so to speak, were like, oh, don't do that. You know, if you do that, it'll kind of blow up our whole field type thing. And so I decided, you know, why build a product basically where none of the customers want it? So I went off and have worked on other things for many years. And then about a year ago, I kind of had a sort of a small methodological idea that basically led me to think, oh, I better think about this physics stuff again. And a couple of young physicists started working with me. And then we started trying to figure out, you know, can we actually work out how physics fundamentally works? And the absolutely amazing thing is that it's clear we've succeeded. And, you know, there are many, many details, many things to figure out. But basically, if you ask the question at this point, sort of, what is the fundamental low-level machine code of the universe? We pretty much know how that works. And it's really exciting. And it's, you know, I keep on telling my sort of co-workers in this area, it's not supposed to be this easy. You know, right. It wasn't, because what's happened in physics about 100 years ago, sort of 2 big paradigms for thinking about physics were originated. One is general relativity, Einstein's theory of gravity. The other is quantum mechanics. And those 2 paradigms that have been kept rather separate have both been really successful, but we don't know what's underneath them, or we haven't known what's underneath them. And what's become clear from what we've done is we now know what is the sort of low-level machine code that lies underneath those theories. And we're able to derive just an amazing amount of stuff about how physics has to work. And you know, for me, it's like, okay, so that's nice. Why do we care? It's kind of a thing, you know, is it going to let us build warp drive? Is it going to let us, you know, solve some current societal problem? No. You know, this is the low-level machine code of the universe. We're talking about what happens at, 10 to the minus 100 meters, things like that. That's the, that's the size of a proton is 10 to the minus 15 meters. So it's unbelievably much smaller than the size of a proton and so on. And so, these are things, but I've been wondering myself, actually, so what do we, so we now have a pretty good path to understand kind of fundamentally how the universe works. What bigger thing do we take from that? And I kind of realized that it's it's an interesting replay of another time in the history of science, which was kind of the things like the time of Copernicus 500 years ago, where people had the idea before Copernicus that, gosh, by just thinking about it, we can work out how the world has to work. And one of the big things that Copernicus established is that by doing a bunch of geeky mathematics, you could have a different view of how the world works, where things weren't things that you could immediately yourself understand. Like it didn't seem reasonable to people that the Earth wasn't standing still, but yet this geeky mathematics could make it work out to have a theory where that wasn't the case. And in a sense, what the result of sort of the whole Copernican story was, people started believing, believe the science, don't believe the common sense, so to speak. And that's been kind of an important theme that we see, increasingly in modern times, is, forget what your common sense might say, the science is going to give you the answer. So, and that's been kind of so that's that's an important thing that came out of kind of the whole Copernican revolution, so to speak. The number of people who cared about the details of the actual mathematics that Copernicus did was very small compared to the number of people affected by that kind of philosophical shift. And so I've been sort of curious for what we're doing. I think the actual underlying kind of formal structure is really fascinating. I think it's really great. We can figure out a bunch of things in physics, but I'm not under much illusion that that stuff in and of itself is of great societal significance. I think what is of potential great significance is the realization that this kind of computational paradigm that we have is kind of the thing that says, people might have said, well, the computational paradigm is interesting, but maybe there are other paradigms, et cetera, et cetera, et cetera. But if we know that that's how our whole universe works, it gives kind of a more serious grounding to, you better take this computational paradigm seriously.
So the idea with the computational paradigm as compared to sort of the mathematical paradigm that we've been using for the past few hundred years is, in the mathematical paradigm, we're somewhat directly getting at these equations that govern the evolution of particles and forces and so on. But we're sort of measuring or discovering these equations somewhat directly. And your computational paradigm is more like, we're taking a lot of guesses, systematically taking guesses at much lower level, sort of computational formalisms, and then seeing what results from them and seeing which ones produce the right sort of things.
Quite. I mean, so there's several different things. I mean, so mathematics is kind of a formal framework. And there are certain ideas in that formal framework, things like numbers, things like algebraic functions, things like calculus and so on. You can think of those as kind of building blocks for models of nature. And they've been pretty successful. But the question is, are they all you need to use to model the natural world? And the thing that I've long suspected is there are more general kinds of rules that you might use to model the natural world that work better than these ones that happen to be embodied in things like calculus. And so kind of the starting point for sort of the computational approach to really everything, not just this fundamental physics, is say, use different building blocks, use programs as building blocks to make models of things. And there's a more technical issue, which is, okay, so you ask, well, what kinds of programs? So the sort of the big breakthrough, I suppose, in this physics project is understanding what kinds of programs can lie underneath space and underneath time, from which concepts like space and time can emerge. But in the end, the important feature of the fact that it's computational and merely computational is the following somewhat technical thing. So there are things we can imagine a digital computer to do. There are things we can imagine, if you take whole numbers and you are doing operations on them, there's certain kinds of things you can work out. in mathematics, we imagine that we can pick something X or something, and X can be an absolutely precise real number. It's not just an integer, which is a discrete thing. It's a number, 1.7846, et cetera, an infinite number of digits that that give you sort of an exact, precise numerical value. Well, one of the consequences of, so if you believe in that, the kind of the structure of kind of the way we think about computation no longer works. And one of the questions is, in the universe, can you have exact numbers like that or not? And so the place where one first sees that issue is something which has kind of been around for a couple of thousand years, which is the question of how does space work?
Yeah,
so,
is it continuous or not?
Right, so like Euclid, his very first kind of common notion when he kind of tried to write down the axioms of geometry was, a point has no extent. You can put a point anywhere. Now, if you imagine, so you take that point of view, it's like space is continuous. You can put that point anywhere you want. So by analogy, you might say, okay, what about let's say we have a material like water, for example, and we say, or some, piece of carbon or whatever else. We say, can we put a point? Can we have something anywhere? Well, the question would be, did you hit an atom or did you not hit an atom? It's the material is made from discrete atoms. So the question is space ultimately made from something like discrete atoms, or is space like Euclid imagined it, where it's just this thing that can be described with mathematics? And one of the things that's come out of this physics project of ours is really good evidence that space is sort of made of not atoms of the kind that we make materials out of, but it's made of discrete things.
It's discretized, yeah.
I mean that. So what it means to say that the universe is computational is ultimately to say that the things that are going on in the behavior of the universe are things which, with a sufficiently large computer of the kind that our computers are today, we can reproduce the universe. It's not obvious that will be true.
Yeah, it's finite precision.
Yeah, I'm interested in how your current work relates to some of these mathematical paradigms that have come before. I know you've said before you're still interested in questions like how do quantum field theory and relativity get reconciled? You, as I understand it, are trying to think about how you can derive things like relativity from your paradigm or your framework.
Yeah, that part we figured out.
Yeah. Oh, okay. Well, so my question here is, how do you decide how you are engaging with the mathematical paradigm, and when are you just scrapping what came before and trying something completely new?
Right. So that's a really interesting question. I mean, when I started pursuing this, I thought we have this computational direction, and it's kind of a different prong of intellectual development from the kind of traditional mathematical physics direction. I thought, we were going to end up finding that, well, we've got this direction. If it works, great. That means we kind of throw away the mathematical physics direction. This isn't true. Turns out an amazing thing has happened. There are all these kind of pretty abstract ideas in mathematical physics that have been floating around. They haven't really connected to the experimental world, but they've been floating around as kind of mathematical structures. They're interesting, deep, rich mathematical structures. Not clear how they're tethered, so to speak, how they're anchored. Okay, so the remarkable thing that's happened is this theory of ours seems to connect to almost all of these. So in other words, what happens is it's sort of a Rosetta Stone. It's a kind of concrete Rosetta Stone to which all these different ideas of mathematical physics seem to connect. And there's a historical analog of this that I find kind of interesting, which is in the early days of the theory of computation, in the 1930s, there were various models of how one might think about computation. There were things called combinators. There was a thing called lambda calculus. There were a thing called post-canonical systems. These were pretty complicated abstract things. And then along came Turing machines in 1936. And this history wasn't quite as simple as this, but in rough terms, they were a more concrete way to think of the idea of computation. And it then turned out that all these other things that people have been thinking about were all eventually equivalent to that. And that's kind of what we're seeing now. which is really neat. I mean, it's not what I expected, but it's really neat. And it's that what's happening is we have this kind of low-level machine code for understanding what's going on. But when you look at it in different kinds of ways, what you see is that you can describe what's happening in terms of these existing mathematical physics ideas that have come before. And that's, it's powerful because we can use all of that mathematical physics achievement. It also allows those mathematical physics ideas, we can generalize many things which have been thought about there. We can give kind of a grounding for why is this true? And that allows those to advance further. And so this is the dynamic right now that we are starting to see happen and that I'm hoping will accelerate, is people making all these connections. It's like, gosh, this is, in some limit, this is string theory. In some limit, this is like loop quantum gravity. In some limit, this is like conformal field theory.
So these convergences help you decide where you engage the pre-existing paradigms as well.
Yeah. Well, I mean, as a sociological matter, we just wrapped up our, we've been doing kind of a summer school about science and technology for 18 years now. And this year, we kind of had a fundamental physics track, and we had, I don't know, 30 or so people in it who are all sort of physics type people. And we just wrapped that up, and we're just starting to try and map out kind of how that group of people becomes kind of the founding group for sort of this project as it goes forward. And I think that it's really, it's an interesting question because, okay, so, I've worked in a bunch of different fields, and I've sort of ended up, for better or worse, being kind of introducing sort of big things in these various fields. And so the big question is, how many pitchforks are there that show up when you come into a field and you say, look, I've got some big new thing to say. And, some fields are heavily pitchforked and some fields are not so heavily pitchforked. And I think the thing we're seeing in this case, which is quite interesting, is, okay, so I should give a little bit of background. So about 18 years ago, I put out this book called The New Kind of Science, which is primarily about kind of the abstract idea of exploring the computational universe of possible programs and using that as a foundation to do science. And in a sense, that book was sort of the effort to say, okay, there's been 300 years of basically using mathematical equations as the raw material to make models in science. Let's try something more general and new. And so at the time, it's like, okay, is this going to work? We've had 300 years of one kind of paradigm. Can we introduce a new paradigm? Well, I think it's fair to say we absolutely won. If you look at, new models that people make of things today, only 18 years later or whatever, and there were other things going on at the same time as my book, which probably helped with this. The vast majority of new models that people make of things are not based on mathematical equations. They're based on programs. So it's kind of the big picture is there's been 300 years of, if you want to make a serious model, write down an equation, to if you want to make a model, write a program down. So that's kind of an exciting thing. And it's the thing that, we've had sort of 300 years where kind of mathematical science has been the aspiration of most areas of science. I think now it's a kind of computational X that is much more the aspiration. So that's interesting. But when my book came out, one of the things, there were pitchforks. And as I look back 18 years later, I hadn't really analyzed this too carefully at the time. The primary source of pitchforks was one field, fundamental physics. So people in other fields, people in economics, people in mathematics, people in biology were like, great, new models. This is terrific. Let's go use them. But in fundamental physics at the time, that was there was kind of a fair amount of pitchforkery. And the thing that I found, the thing that was kind of bizarre to me about that was my personal history kind of made that odd. Because personally, when I was a teenager, I was a physicist, and I was a pretty successful physicist. I think the people were sort of a little bit, I don't know, shocked when I kind of left physics in a sense and started working on these computational kinds of things. And they're like, you're a good physicist. Why aren't you going on working on physics? Well, I had the good fortune to kind of live through a time in the late 1970s when physics was kind of having a golden age, when, you know, there was a lot of new stuff that could be done, and it was really cool because, you know, I was a, whatever, 16, 17-year-old kid, and I was writing these papers, and people still read these papers today because I was involved in the field at a time when it was kind of in this rapid growth phase, and, you know, lots of low-hanging fruit was to be picked, and I got to pick some of it. But then, you know, whatever, you know, 20 years went by, and then the people who were sort of my colleagues, who were mostly a bit older than me, were like, oh, you know, you're coming to take all this computation stuff that you figured out, and you're going to come back into fundamental physics. Oh my gosh, you can't do that. Please don't do that. You know, it's going to blow up our field.
You'd gained outsider status to a degree.
Yeah, yeah, right. But it was so weird because it was kind of like I was the quintessential insider in some sense, because I, you know, I knew the field well, I knew the people well, but what had happened was at that time physics had pretty high self-esteem. That is, there was a, you know, string theory was still going strong. You know, it was like M theory is going to give us the answer. It was, you know, we're almost there. And
this is the, are you speaking about the late 70s or the early 2000s?
No, I'm talking about 2002, that kind of time frame.
Okay.
So what happened in physics was, you know, this idea that there had been kind of a, in the early 70s, quantum field theory really looked like it was going to work. And there was a big run of quantum field theory to the end of the 70s, basically. And a lot of things got figured out, and it was really a great period. It was kind of the machine learning of its time, so to speak, of, you know, new results every week kind of thing. And then it kind of, you know, it kind of petered out. You know, the things which the low-hanging fruit had been picked, and the things which were then sort of the hope for what was going to happen, it wasn't, you know, it wasn't like we're getting further into kind of figuring out what's going on. There were, you know, there was progress made, but it was much more incremental. And I think there was sort of a rebirth of optimism in physics in the connection with supersymmetry and string theory and so on, which kind of was still rolling by the early 2000s. I mean, now, if you ask people, it'd be interesting to do actually, if you say to people, who thinks they're going out and trying to find a fundamental theory of physics? It's like, physicists don't think that. They think they're working on some mathematical idea that is going to lead to this, that's going to lead to that. And they're right. They're working on very interesting stuff. It's very valid. It's nothing wrong with it. But it's not like, we're almost there, guys. And so I think, you know, in a sense, our project is, you know, it's not like there's 5 competitors for, no, we're almost there. Whereas I think in 18 years ago, it felt more like, you know, we've almost got it.
So
but I think
the reception is different now.
I think so. I mean, I think, you know, it also helps that there's social media and things like that. It helps that, you know, I'm choosing to do this project in a very open way. So like we're live streaming all of our working sessions and so on. And, you know, it's like people know that, you know, if they say, oh, there's this terrible thing about this project, it's like, well, you know, we'll discuss it. You know, it's not like it's a invisible, you know, it's one, you know, missile that's launched and then another missile gets launched back type thing. It's just like, it's a thing that can be interactive, which I think is a feature of modern times.
Yeah, I'd like to explore a little something you mentioned there, this golden age of physics that you've talked about. So, you know, at Palladium, one of the things we focus on is the idea of functional institutions. You know, what are the institutions that build our political norms, our material progress, and so on? And you've mentioned before that particle physics, kind of in this golden age you've mentioned, was running in a lot of ways on the fumes of the Manhattan Project. And kind of carried through for a few decades and started stagnating around the 80s, the end of the 80s. You had a lot of personal experience with this. You studied under Richard Feynman and others. I think what we're interested in here is what made the field work then in its heyday, in this golden age, and why did it stop working?
So I think the general pattern that you see in science and in technology as well is there are these moments of methodological advance. There are these moments where some methodology gets invented or starts working. And then there's a bunch of low-hanging fruit to be picked. That's opened up, things are opened up by that new methodology. And that's kind of what happened in particle physics in the 1970s. this particular methodology of using quantum field theory and so on opened up. Now, what was the institutional structure around that that made that a fertile field? That's an interesting question. In other words, you know, there were physicists knocking around who were ready to kind of receive this new methodology, so to speak. And yes, a lot of the sort of the presence of physics was as a result of the Manhattan Project. And, you know, I knew many people who'd been involved in that. There was a kind of a general growth of physics. Now, it's a tricky, I think that, you know, from my sort of experience and study of the history of science, I think these methodological advances are much more important than the societal structure that exists within these fields at the time when the methodological advance happens. I think it's really a question of now it's possible to do this. Now we have this idea that really opens up a lot of possibilities. Now, what can kill that societally? You know, it's funny because it's a big careful what you wish for situation, because what I think kills it is the size of fields. That is, at a time when, you know, when there are a bunch of, you know, when there's like 20 people working on this thing. You know, look at the early days of quantum mechanics or something in the 1920s. There were a limited number of tens of people working in this area. And then, you know, and you say, well, you know, everybody can kind of run along. It's very entrepreneurial. Some of what's done may be crazy. You know, some people, there may be individual people who have all kinds of fights with each other, all these sorts of things. But it's a small, agile group. Okay, then the field is successful. And then people say, oh, there are, you know, 10,000 people who get their PhDs in this field, and we've got to have a professional society, and we've got to have, you know, funding channels, and we've got to have, you know, departments at universities, et cetera, et cetera, et cetera. Then what happens to the field? Well, it's a necessary feature of a big field that it has to have kind of, you know, all sorts of structure and checks and balances. And it's like, what does it mean, you know, when somebody enters the field and makes contributions, how do you assess the contributions? How do you pick the people to give the funding to? All these kinds of things. And I think this is the, you know, in a sense, the thing that slows fields down is when they get big, because it actually becomes harder to innovate. You would think, oh, you've got more physicists, there's going to be more innovation that happens, but that's just not true. I mean, what happens instead, in most cases, is that, you know, the sheer size of the field causes there to be structure that basically makes it much more difficult to innovate in certain ways. And so, you know, one of the things that tends to happen is you basically have to bud off a new field. And that's where the innovation has to happen. And it's a sort of separate.
And the new field is often another small working group, it seems like. It's a new community of research, so to speak.
Right, and I mean, I think that, you know, you saw that, well, when computer science kind of budded off from electrical engineering and mathematics, you saw that when molecular biology kind of budded off. You know, there have been different kinds of things like that. And I think, you know, you know, in a sense, well, I consider that I made a mistake in the 1980s with kind of the field of complexity, which I think sort of incompletely and rather, you know, not very beautifully kind of budded off from other kinds of things. I mean, I was, you know, for me, you know, I had made a bunch of discoveries about kind of the basic science of how complex behavior can arise from very simple systems, very simple sets of rules. And I thought, this is really neat. This is really interesting. Has a lot of implications for a lot of different fields. Let's, you know, build this new area of science that is all about that. And I think in retrospect, I made a sort of a structural mistake, which was that if you look at a field like mathematics, there is a field of pure mathematics. There's a field where you just do mathematics for its own sake. Right. Then there's the applications of mathematics, where it's like, well, we're going to use mathematics in economics and biology and medicine and whatever else. But those are separated from this core field of mathematics for its own sake. And what I failed to do, I think adequately, was to kind of sort of encapsulate complexity, or whatever it should be called, you know, kind of studying the computational universe as a pure field for its own sake. And
was it just not mature enough at the time, or how did you make that mistake?
By not thinking about it clearly enough, to be honest.
Okay.
I mean,
so
I think
you could have gotten it right at the time, but it
maybe. I mean, you know, what happened at the time, you know, like I started the sort of first journal and the first research center in this area. And I should have made it much clearer that we're just going to do this pure field. But there's a lot of pressure to say, let's do applications. Look at all this cool stuff you can do in economics. Look at all this cool stuff. You can work out the hypersonic reentry of the space plane with these kinds of methods. And it's like, and by the way, that's where a bunch of the funding for things comes from. Because if you're going to invent a new field that's a pure field, it's like, why would you do this field? This field is a pure abstract intellectual field. Why would you do that? Well, you do it because, it's got these applications here and here and here. Now, if you look at the history of things, mathematics was really lucky because mathematics managed to squeak through as a pure field of intellectual endeavor, kind of on the back of education. So it's kind of like the fact that there are people doing now, another field that could have squeaked through was logic. Back in the Middle Ages, people would learn mathematics, they would learn logic. Logic didn't get sort of the applications that mathematics got in science, and logic didn't, and that meant that it didn't kind of have the selling points for education that mathematics had, and it kind of fell away. And it didn't become kind of people couldn't justify sort of just working on that as a pure field. Now, I think that, for example, in the things that I've studied about sort of the computational universe, it's very interesting because when people do a kind of good foundational piece of work in studying the computational universe, they figure out something about some weird, tiny little abstract system. I know deterministically one day the thing they figured out will be picked up as a model for something and it'll be important. And so, for example, one of the things that I found amusing, I studied these things called cellular automata, and there are 256 of the very simplest kind of cellular automata, okay? And so for a while I still have paper files, I used to have a file folder for each rule number. And I would just put in, when there was a paper on an application of Rule 18, I would put it in the Rule 18 file folder and so on. And there were, what was happening was these were extremely minimal models. And so it was sort of inevitable that they would end up becoming useful for something. But you might have said when you were going to study them as basic science, why would anybody care about this? This is a very, it has all kinds of structure, but it's like you're studying it for its own sake. I mean, my kind of, like Rule 184 was like, I don't think this is going to be interesting for anything. Well, I wait a number of years and it's become the standard minimal model for road traffic flow. And it's like, okay, that's a, but the fact that it existed and we knew a bunch about its properties and we understood a bunch about it was why it was able to be picked up for that application. And, so in a sense, that's we've got nice examples of where by studying the most basic science, we are having the sort of highest leverage things figured out that can then later flow down into applications. But selling that as a thing on itself, that's difficult. And I think that, in other words, to say, we're going to study this basic thing and 20 years, 30 years, whatever from now, this thing will flow down into something important. I think that that's
hard to judge.
It's hard to judge, but, honestly, it's if you're in the, a thing that has been very clear to me is, there's a certain aesthetic of simplicity, which makes that possible. And it's kind of deterministic, actually, if you kind of know what you're looking for. But at the time, this was mid to late 80s, it was like, there was no way that one could, I mean, I probably should have made a bigger effort to just say, it's really worth doing this as basic science. But the justification for basic science, in society is pretty complicated. I mean, in other words, why should you do it? Why should a society do it? And what I've noticed is the sort of there's a principle. If you have an area, if you have an entity that has sort of a monopoly in some area, and there's a basic set of questions about that area, well, it's in the interest of that monopoly to explore those basic questions because that monopoly is the only thing that's going to benefit. So this was what happened with Bell Labs. It's what happened with IBM for a while. It's like, if you are sort of the, you might as well investigate transistors because, yes, other people can probably use transistors, but, if you're running the telecom infrastructure of the US and so on, you're going to be a primary beneficiary of even basic research. And I know, even in my own company, for example, there are things about mathematical algorithms where I pretty much know, we're the only folk who have sort of the distribution channel and the positioning to make use of things which are essentially basic science advances. And so
that's through Mathematica and Wolfram Language.
Yes. Yeah. I
mean, so going back a little bit on what we were just discussing about like how these fields kind of get started and justify themselves, especially in the beginning. I guess to synthesize, it's the major payoff is sort of over the long term, right? You're doing basic science, it pays off in the long term, but it needs to have some niche at the beginning that allows it to get started, right? Because
that's one of the theories. So, for example, take cybernetics as an example.
Right.
Cybernetics was killed by its niche. Okay, so its niche was control theory, which is a perfectly valid, sensible area of engineering, but the lofty goals of cybernetics were completely squashed by kind of the practical applications of control theory and so on. And I think having too good a killer app early on is actually very damaging to basic fields.
It wrecks your focus.
Right. Well, and also it just it becomes all about that, right? And so, I think one of the things that's very interesting with our physics project is I think we may finally have the opportunity to get kind of the basic science of the computational universe to be an important thing, because people now can see that is the underlying stuff that allows you to do this also very abstract thing in physics. But people kind of know that, or at least some people have the view that, well, we kind of know why we know why we're doing fundamental physics. Now, it's not completely clear why we know why we're doing fundamental physics, and it's kind of shocking. I was writing about our project, and I thought I'll write sort of a basic outline history of people's attempts to find the fundamental theory of physics. And I thought, gosh, this is going to be really hard to write, because I know this history reasonably well, and I'm thinking there's going to be so much to write about. Actually, what's shocking is how little there is to write. In other words, throughout history, the number of times when people have really cared about the fundamental theory of physics is surprisingly small. Philosophers discuss it from time to time. People say, physicists in a sense say we're almost there a number of times, but it's not something which is kind of a core focus. I mean, it's a little bit like if you're a biologist, understanding what really is life, or what was the origin of life.
Right.
It's amusing, but it's not what you do every day.
Right, the application. Well, this comes back to the question of like the application. You say you've found some formalism or some computational model that allows you to derive things like general relativity and quantum mechanics. Yep. So the application of that, like practically speaking, I mean, you said you weren't expecting too many practical applications, but one of them would seem to be like wherever there are those sort of interactions between quantum and gravity, like there would presumably be something, because those things currently have kind of sort of contradictions and incompatibilities, and
sure,
but it might not, I guess, end up in anything sort of practical technology wise or something.
Well, yeah, I mean, we can say a lot of cool things about phenomena that happen in the mergers of large black holes.
Right, or like in cosmology, the first few moments of the universe, presumably.
Yeah, we probably have interesting things to say about that. But the problem is, we don't have any. I don't have a pet black hole. I mean, it's some.
It's
these
abstract.
Yeah, right. I mean, these are things that are very interesting, and very, and it's sort of a question for a society. It's like, okay, it's like we're climbing the Mount Everest of science. Where maybe we'll, I don't know how long it will take us to kind of get to the summit, but I think one of the exciting things, I think we're on the right mountain now, so to speak.
Right.
And the question is, how does society value, what is the importance to society of reaching the summit of this particular intellectual mountain? And one can certainly, there's a certain kind of pride of achievement that a society can have of, gosh, look at this amazing thing we figured out. I don't know how far that goes.
Yeah.
I think that, one of the things I found interesting is the engagement that we've had from kind of what I might call the general public, so to speak. I mean, people seem interested, and people seem, I think that people are interested at the level of sort of a philosophical level and at a almost an experiential level. I mean, like these live streams we do where we're just doing, working sessions talking about highly technical mathematical physics and so on. People seem to find those interesting. I mean, it's kind of you're getting to see kind of something which people never usually see, which is actual science being done kind of in real time.
Right, and especially right at the root of a new field where often the most interesting parts are being done.
Right. And so I don't really know, I think it's I hope sort of good entertainment in some sense. It's kind of fun for us. It's kind of, it keeps one a little bit more focused, and it's kind of interesting to realize that, these crazy things we're thinking about, it's like people are watching, people are commenting, we're recording it, et cetera, et cetera, et cetera. It's kind of, actually, we're about to dump on the world 700 hours of recordings of all of the kind of working sessions that we had, working up to the announcement of this project. But I don't completely know what to do with this. I mean, it's kind of like, it's an interesting thing because we're kind of letting people see inside the process of science. And, what consequence does that have? I'm not sure yet. I mean, I think that, does science become, is science a branch of entertainment, so to speak?
Right. And this is kind of coming back to the niche question. This is sort of the niche you're currently riding on, is it's entertaining, at least for you and the people working on it. It's inherently interesting, but then also for a bunch of people watching and so on. But coming back to your note that sometimes a killer app actually ends up killing the field, are you worried that if this finds like too fruitful of an application in physics, that it might end up coming back and sort of killing the more general idea of this computational paradigm, or taking it astray for too long?
Let me distinguish a couple of different things.
Sure.
Okay, so the computational paradigm that is leading to computational X for all fields X, that simply is the dominant paradigm of the century. And there's nothing we can do will mess that up.
Right.
Now the question is, that is like saying the idea of mathematics was a dominant paradigm of the science of the 20th century, for example. And but that is a little different from talking about kind of the pure mathematics itself. The computational paradigm, and I've spent the last 40 years or so developing this kind of computational language to express computational ideas to make it possible to do computational X. I mean, I kind of view a lot of what I've been doing with Wolfram Language and so on. It's like making a notation for talking about things computationally, in sort of the same way as mathematical notation made a notation for talking about things mathematically. And that's a very practical, very kind of broadly applicable thing that sort of nothing we do in our fundamental physics project or studying the computational universe, it's not really going to derail that. What studying the computational universe is doing is it's providing sort of basic science underpinnings for the kinds of things which will eventually trickle down into the computational X fields for all X, so to speak. Just as pure mathematics has provided things which eventually trickle down into the mathematical science fields. So it's sort of a separate branch. And so the question is, in that separate branch, is it going to be the case that there's sort of killer apps for that sort of pure basic science area that kind of derail it? I think I kind of learned from my earlier mistakes. I mean, I think, we'll do what we can to prevent that happening. I think that the thing that is sort of encouraging in a sense is that we're just starting to see. So we got this definite sort of approach to models of physics. And what we're realizing is that actually you can sort of take idealizations of that model. So you have a model which is itself kind of a very abstract thing, but you can take sort of simplifications of that model and study those to understand some features of physics, but those simplified models can be studied on their own, and those are kind of some of the raw material necessary to kind of study the sort of basic science of the computational universe. I mean, I think that it is really an interesting thing that, at what point will this sort of, I know perfectly well that, you know, there are 100,000 good PhD theses to be written about kind of the basic science of the computational universe, which will ultimately have high leverage and have, you know, the sort of a trickle down effect. But how do you get there from a kind of institutional point of view is interesting. I mean, the thing to understand about the computational paradigm is, for example, when it comes to education, it's probably the first major new paradigm to have come into existence since the beginning of public K through 12 education. So it's about 100 and something years old. And, you know, you study reading, writing, arithmetic, and so on, but you didn't study computation in, you know, 1890 or something like that, or not what we currently mean by computation. It just didn't exist. That paradigm did not exist. And so it's, and when it comes to universities, they have a, you know, a certain structure with certain departments, et cetera, et cetera, et cetera. It's an interesting thing to see, you know, what does it take to have a kind of a new paradigmatic direction in basic science come into existence. I mean, by the way, at universities, we can already see the sort of creaking issues because, you know, like I talked to a bunch of university presidents and things, and they are often bemoaning the fact they say, oh my gosh, you know, all these people who are coming to our fancy university, 70% of the incoming students want to study computer science, but we only have, you know, only 5% of our faculty does computer science. What should we do? Right. Well, what's really going on there is we want to study computer science as a proxy for we want to use the computational paradigm in doing whatever we do.
Right,
and computer science actually isn't mostly about the computational paradigm. Computer science is about the specific, you know, how to program. It's about specific methods that have been developed in the field of computer science. It's not about kind of the general directions of using computation in different fields. And so but you know, that kind of issue is an interesting one that I think is structurally is something that is kind of a bit of a wake-up call for there's something a little bit wrong with this picture. You know, what's going to happen here?
So you would have to ideally sort of redraw the boundaries a little bit as these fields have matured and changed over time. Like it might be that, you know, computer science as we know it now maybe has to be carved up into a few different fields because there's actually just multiple things going on there.
Yeah, or they're integrated into the existing fields in various ways.
Right. I think the thing is what one has to do is there's really a computational X for all X. And the real question is, does that become a separate department of computational X, or is computational X absorbed into the department of X?
Right.
Okay. And structurally, that's an interesting problem because, you know, for example, when it comes to educating students, there's a certain minimal sort of knowledge about the computational paradigm that's needed to be able to do the computational side of computational X. Just as there's a minimum level of mathematical knowledge that's needed to, you know, deal with lots of fields which have mathematical pieces to them. It's not clear how you teach that. It's, you know, the computer science department is basically not set up to do that. It's not what computer science departments do. I mean, I think one of the things that's sort of a little, you know, it's kind of an example is, you know, in a sense, computer science departments, it's like a little bit of it is writing you know, how to write a program, things like that.
Right.
And it's kind of like, you know, you teach people to write and you have a certain amount that you can do in teaching people to write. But at some point, to really make progress, you have to have them writing about something. Right. And, you know, I think this problem already existed in ancient Babylon. You know, they had scribal schools and they would teach people to write. And then they would break it into, you know, I think 5 or 6 areas where it's like, and now you're going to learn to write about this, 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 and this. Right. But, and that's kind of the taking the computational paradigm and importing it into these different fields. But I think that's you know, that's an interesting, to me, that's much more of an applied problem than what we're dealing with kind of studying the computational universe, which is the pure mathematics end of this computational paradigm. There's the computational paradigm is a very practical thing that's going to be fed to all these different fields. And then there's what's the intellectual foundation of this? Well, if you go far into that intellectual foundation, you get to this kind of science of the computational universe and so on.
So I have to jump in here. Sorry. We're looking at a lot of audience questions here. I know that people on a lot of the different topics we've covered are going to want to dive into some of these issues. Just a reminder to the audience, put all your questions in the Q&A box, not in the chat. We're not going to see them if they're in the chat. And you can also upvote questions that you want to see asked. So Wolf, do you want to get us started with the first question?
Sure. So Stephen Pimentel asks, as a private company, Wolfram Research has had many advantages, but what limitations has it faced as a private company in comparison to other institutions?
Right. So, well, there are two parts to that. There's the word private and there's the word company.
Right.
And they're both important here. I mean, I've been lucky enough, I started our company 33 years ago now, and I've been fortunate enough, touch wood, we've been profitable every year for the last 32 years, which is nice. Thank you, world. It's, I think that we partly achieved that by the very boring method of spend less than you make. And that generates limitations. And, but the great thing is that as a kind of private company that doesn't have to answer to investors or to the public markets and so on, we've been able to do things that are really very long-term and very, to the outside world, insanely risky. So, lots of projects we've done, people would have said, like, I don't know, building Wolfram Alpha, for example, people will have said, you just can't do that. It's, people have tried it, it's just not possible, et cetera, et cetera, et cetera. I was in the fortunate position that the only person in a sense that I had to convince was myself. For me, it was like, I think we're going to be able to do this. So let's go ahead and try it. And I think it's been great that we've been able to do things that have 10-year, sometimes longer time horizons. I mean, in a sense, and that we've kind of only had to answer to ourselves, so to speak. That's been a really good feature. The disadvantage is, I have sort of set things up so we really are focused on, making great products, doing great and interesting R&D, rather than sort of maximizing the commercial side of the business. I'm always, it's kind of, and it's been a complicated trade-off, because it's like we could have made, 100 times as much money probably by focusing on, and you talk about killer apps and their effect on science. Same thing in our sort of technology area. There are things absolutely we could have done where it's like, yes, absolutely, we can double down on this thing. We can really push this hard. It just happens to be intellectually pretty dull as far as I'm concerned. But it would have made us a bigger company. So I think that the thing that's just great about a private company, is you kind of get to make your own decisions and your own mistakes. The other thing that's great is that it's a managed entity. So at a university, for example, it's like nobody tells the professors what to do. I've seen many people at universities, friends of mine, they get tenure, they go, there's a big struggle to get tenure. And then it's like, well, I guess I just have to figure out what I'm going to do now. And, there are cases where it's like, if some manager just told you a little bit, hey, you should go in this direction, you would be very productive. But as it is, you're kind of free running, and it's like, oh, well, it's kind of, you lost focus. So I think it's really, one of the nice things about a company is that it does have some sense of direction. I mean, I've seen, a bunch of research institutes and things like that. Often when they get founded, it's like there's a great thing going on, but after, decades go by and so on, it's like, well, what's really the point here? We're just sort of supposed to do research, and, what are we supposed to do research about? How do we really figure out whether this makes sense, et cetera, et cetera, et cetera? I think the notion of we're a company which ultimately is trying to make things that are useful and that people are going to buy is a good thing. And I think, certainly this physics project that we've done, really the efficiency with which this project has been done, kind of outraged even me, in the sense that, in 6 months, we managed to, I wrote an 800-page book. We managed to sort of grind through just an amazing amount of science. And, if you say, how was that done? Well, there's some smart people working on it and all that. But also we have this whole structure of, of things where we built a lot of automation in our technology, but we also, have project managers, and we have, things where when something gets, we have some structure that allows us to sort of make progress. And that stuff doesn't tend to exist in universities because, for example, in a company, I always, people who've been like in the academic sector, they come to work at our company and they're like surprised that, this, I don't know, the system administration group is like their goal is to make people at the company as productive as possible. It's like, that's shocking, because in academia, it's like the role of the system administration group is often to sort of make the system administration group have a good time, so to speak, because there isn't really a, there isn't this notion of, we're trying to make something here. So I think that's been it's a good, I would say that if, I've been fortunate that the things that I've been intellectually interested in doing are mostly things that ultimately are useful to the world on a fairly short-term basis, and that you can essentially have a self-sustaining economic structure around them. The physics project is not an example of that. And this is causing
I'm going to jump in here just because I want to keep us moving on questions as well.
Yeah.
On your physics project, though, we have one here going a little bit more into the weeds, maybe. John Doolan asks, one of the great failures of string theory and its various subfields was their inability to provide falsifiable predictions of new physics. And he asks, how can your computational approach avoid that fate?
Well, as far as, okay, so the typical pattern in the history of science, when a new sort of paradigmatic approach comes along, the first thing you do is you make theoretical predictions. That is, there's a lot of stuff that's already known. Do we reproduce what's already known? We're primarily at that stage right now.
Right.
The fact is that typically in theories, one of the dangers is to think you have too many predictions that are sort of experimentally verifiable too early. Like, Einstein with his theory of gravity came out in 1915. If he had had somebody go do the experiment on the bending of light around the sun in 1916, as almost happened, they would have said the theory is wrong, because the calculation that he did, his theory was correct, but the actual calculation of the physics of how light bends around the sun, he got wrong. And so, and similarly, when Newton was doing his, theory of gravity, he has this whole book and he's describing all these things and he calculates the motion of the moon and he gets the wrong answer. And it's like, so you might say, oh my gosh, I should, Newton might have said, oh my gosh, I should abandon this whole theory because I got the wrong answer for this. Turns out it's a really hard calculation. It took another 150 years for people to get it right. So it's, it's a complicated thing going into the kind of the actual, let's go actually get something that somebody can turn a telescope in this direction and go find it out. Now, it looks like we are getting a few of those kinds of things that are starting to emerge, but they will be complicated, and it'll be a complicated issue of knowing that even given the underlying theory, that we got the right predictions and that we turned the telescope to the right thing and did all those kinds of things correctly. And I think it's one of those things not to rush. The important thing right now is theoretical predictions. And one really interesting thing that's happened is, well, this methodology that which I call proof by compilation. So it's basically, there are fields like general relativity, theory of gravity, in which people calculate things like the merger of black holes. But how do they actually calculate it? They actually calculate it by using numerical simulations on computers, et cetera, et cetera, et cetera. With our model, we have a different way to make that numerical simulation, which, and from our model, just from our model, you don't go through general relativity at all. Just from our model, we know that it reproduces what general relativity, we know theoretically that it reproduces what general relativity says, but we can actually do this thing. We can essentially compile general relativity into our models and see that when you actually do practical calculations, you get the answers that the practical calculations of general relativity would give. Same thing with quantum computing, actually.
Cool.
So that's an interesting kind of methodology for, people say, did you really reproduce this theory? Well, let's take the way people actually calculate things in these theories and let's show that directly from our theory, we can go do those fancy calculations, independent of going through this fact that we know it reproduces that sort of intermediate theory.
So let's move on to another question. This one from Samo Buria. He asks, what has been the most surprising experience with your public approach to science so far? Do you think it might result in better transfer of scientific culture?
It's an interesting question. Let's see, surprises. Well, I would say the level of engagement of the public and their level of conceptual understanding of what we're doing is higher than I expected. In other words, things that I thought were conceptually pretty complicated, people are getting them. Even though the mathematics and so on, the formal development, they don't know anything about that necessarily, but they're getting some of these conceptual things that I thought were quite hard. I would say that that's one thing. Another, I mean, there are some details, like one bizarre detail, I don't know what to make of it. Well, okay, I had no idea there were so many kind of amateur scientists who have thought about fundamental theories of physics. That's a weird phenomenon. I mean, it's kind of like, I think, I mean, it's weird, and it's kind of, it's a little bit upsetting to me at some level, because it's like people putting this effort into this, but they just pretty much ignore 20th century physics, which puts you in a huge disadvantage. It's like, you know, what we're doing is leveraging all that fancy stuff that was figured out in 20th century physics. So that's a weird thing. I mean, that there's so many people who have these kind of sort of theories that are like they don't really get to the starting gate, because they're kind of operating from we start from what was known 100 years ago type thing. Another thing I just throw out there, it's just an observation for people who are curious, but even 20 years ago, when I was working on New Kind of Science, there were lots of essentially theological questions that came up about how does this, and one of the things that I've noticed in recent times, I don't know how to interpret it, is essentially no theological questions. You
mean people asking the theological questions, or you noticing the theological questions?
No, people asking them. Asking them. I mean, people were you know, even though, in fact, what's really interesting to me is a lot of the logical development of the early theologians is fascinating in terms of thinking. If one actually thinks we've really got the fundamental theory of physics, we really know how our universe works, a lot of these questions which were asked even in the period before modern science, the kind of logic of those questions is absolutely valid, and you can start kind of trying to untangle those questions, and you know, that go directly from kind of the thinking that happened in sort of early theology to what we're doing in modern science. But it doesn't, you know, that hasn't been a thing.
Yeah, because early thinkers, they're kind of present in both fields, not just Newton, but even later physicists. I was interested in your initial point there on people getting the concepts better than you thought they would. Do you think this means that we've actually had a more successful, like, public school scientific education, or is it despite that people are just smarter?
I don't think this is people understanding what are really kind of abstract concepts. I mean, I would say that these things, you know, this is not about people knowing some mathematical method and being able to see how it works. This is about people following what are really quite new abstract ideas, and kind of seeing what consequences they have. Now, you know, maybe I give myself too much credit for being able to explain the things. Maybe we managed to polish the ideas to the point where they're not, you know, for me, they were hard to get to. And so I'm therefore very impressed when other people seem to get them, because it took me a while to understand these things. And, you know, it's impressive to me that they're things of considerable abstraction and kind of conceptual depth. And that, you know, sometimes one imagines that you only get to the ability to understand those things by learning very formal subjects in school, so to speak. And I think this is sort of a little bit of a counterexample to that. I mean, I think that the level of kind of, you know, it's one of my hobbies is kind of doing educational kinds of things with kids. And I wouldn't be that impressed with you know, the current state of sort of your average school education. I mean, you know, one of the challenges, one of the fundamental things is, you know, a lot of education is about kind of, let's describe what's known and what's true. And the idea, like for example, here's one interesting pseudo-educational experience that I have a lot. So, you know, we make this thing called Wolfram Alpha, which is used by lots of students. And so I'll go give talks at, you know, random schools and things like that. and people will like, who is this guy? Oh, it's, this Wolfram name is there. Oh, there's this thing called Wolfram Alpha. We use it all the time.
Yeah, same
and then
guy.
there's this moment when they realize, oh, wow, this thing that's just, like this technology, this website, there's a human.
Yeah, thanks for getting me through undergrad calculus, by the way.
My pleasure. But yeah, no, but it's, I think it's a wonderful moment actually, when people realize this thing, this technology, this kind of disembodied technology, there's actually a human who had to make that, or who had to, cause it to get made. And it's, I think that's one of the things that is, it's a funny feature of education, that people don't understand that ideas get originated. And so one of the things which maybe is we're achieving with this project actually is that people understand that ideas get originated. That is, people read, a history book and they say, so-and-so figured out, Einstein figured out the theory of relativity. Okay, fine. They sort of read that, but now the theory of relativity just is. And the concept that there was some sort of real human process that got us to that point is lost.
Right.
And, often when you read the history of science, one of the things that there are two mistakes in sort of that you often deduce from reading about history of science. One is things happen immediately, and the other is people have brilliant ideas. And that's what drives science. And in my personal experience, neither of these things is true. That is, when it looks like, viewed from a distance, oh, relativity was accepted immediately. Well, immediately means 20 years. And, when you're living through those 20 years or whatever, it doesn't feel like immediately. And then, the people have brilliant ideas. It's like there are all these stories of, so-and-so was, sitting in their bathtub and they have this idea type thing. And that was the key moment when the great science discovery was made. That's never true. There's always a 20-year development of people getting into the right sort of conceptual framework, and maybe there's a precipitating event at some point, but the real story is that kind of long conceptual development. Okay, we got lots of other Q&A questions.
So yeah, so on educational institutions, I think that's a nice segue into Matt's question. So you attended Eton and Oxford, you got a PhD at Caltech. What or who do you credit for your own intellectual formation? Were these experiences useful, or was there something completely different that helped you become formed?
Yeah, I mean,
or now.
I'm an obstinate, independent character in the end. I mean, I think that it's funny because I will sort of say, it's an interesting question. I mean, so, when I was in high school and things, I learned all kinds of stuff about Latin and Greek. And at the time I was like, why am I learning this stuff? I hate this. This is a waste of time. And now, I regularly look things up in in a Latin dictionary because I'm trying to make up words for things. I would say that look, okay, the real thing that probably was my major, what were my formative educational experiences? I suppose the fact, well, I got interested in physics when I was about 10, 11 years old, and the things that I was studying in school had nothing to do with that. So the things I was learning about that, I was just learning on my own. And that meant I wasn't learning it in order to do exercises and get good grades or whatever. I was learning it because I thought it was interesting. And then, I didn't have a reason to like do exercises in textbooks. It's like, why would I do exercises in textbooks? I've got questions I want to answer. Let me just go try and figure out the answers, even though many of those questions may not be questions that anybody had figured out answers to before. But my motivation wasn't. And I think if it had been the case that somebody had said, hey, let's enroll you in a physics class, it might have killed my interest in the field.
Right.
I mean, in other words, it was the fact that I was sort of running it as a kind of an independent thing. I think the other important thing was, in those days, I wasn't that busy as a school kid. I mean, it wasn't, in modern times, I'm often amused that, I'll interact with high school students and so on. And it's like, I'm the CEO's doing a bunch of stuff, but I seem to be a lot less busy than your average high school student. And that, I think the fact that I wasn't super, super busy as a kid in sort of doing my early education and so on, and that meant that I could like spend a bunch of time studying physics. That was probably important. I think subsequently, it always helps when you go to sort of top places, because you kind of the set of expectations about what kinds of things are possible go up. I think also in the fact that I got to know lots of I read lots about physics, and there were all these names in the so and so's effect, so and so the so and so theorem, et cetera, et cetera, et cetera, and I got to know those so and so's, so to speak.
Right,
and the fact that yes, there's an actual human.
Motivational posters of physics, maybe you can see
What's
them
that?
all in the the motivational posters maybe of physics, you can see them all in the equations. I can put my name on an equation, maybe I'll do physics.
Right, it's something like that. I don't know whether I really, it's funny because I mean, honestly, sometimes I would say that there were sort of almost negative motivations, in the sense that there were things where people were like, that's just not possible. You can't possibly do that. And it's like, well, why don't I just go and do it?
Yeah.
I got a certain, I mean, I'm not, one of the things that happens in these fields, and it's sort of a characteristic of I mean, there's this whole question of, do you do something because you want to compete with other people in doing it? Or do you do something, there's sort of a trade-off. If you're in some very popular field where you're competing with lots of other people, if you figure something out, then it's like everybody knows why it's important. You don't have to explain it. I have tended to work much more in areas where nobody cares, at least the time when I start doing it. And when you've done something, you have to kind of wave a big flag and say, this is why you should care about this. But it's much, for me, it's a much pleasanter life. I'm not very sort of competitively oriented. So it's, because I suppose I'm too egotistical to be competitive, in the sense that I like to feel like I'm doing something unique, right? If it's a competition, it's like I know there's somebody else doing the same thing. It's like, why am I doing this? And so it's but it's an interesting question. I think probably the very fact that my kind of education process early on kind of stayed out of the way of the things that I was really most interested in was perhaps the greatest contributor to that. But of course, I learned a bunch of things. Like I learned a bunch of stuff about writing and even like lots of kind of humanities-like things. I learned just because I went to schools where that was sort of the emphasis. And even though at the time I'm like, why do I care? It's turned out that that's been pretty useful over the course of time.
Great. So how about a technical question? So Sam Hammond asks, what's the relationship between your theory's hypergraph and the ER equals EPR conjecture, which suggests the geometry of space-time is emergent from quantum entanglement?
Oh, that's complicated. There's probably a crisper, more technical answer to that you can find on our website in the Q&A section. But the kind of ER equals EPR story is related to our, well, I can say the words, but this gets kind of complicated to talk about. In our kind of model of things, there's this kind of hypergraph that represents space, physical space as we know it. There's this thing we call branchial space, which is essentially the space of entangled quantum states. And it's another kind of space. And these two kinds of space are knitted together through this thing we call the multi-way causal graph. And this ER equals EPR business is all to do with the way that the multi-way causal graph knits together the structure of space and the structure of this branchial space of quantum states. Now, it's just to give, let me not try and go into more technical detail, because I'm going to have to explain ER, I'm going to have to explain EPR, I'm going to have to explain a bunch of things, and it's a little complicated. But it might be interesting to understand perhaps that space, as we experience it, in our model is kind of knitted together out of these sort of atoms of space. It's a little bit like how, you have a fluid like water. It's got a bunch of discrete molecules in it, but the water as a whole behaves like a continuous fluid. Sort of the same kind of thing that's happening in space. And so one of the questions is, of all the things we see happening, so in our model, the only thing that exists in the universe is space. And everything that we experience is a feature, is some kind of detailed feature of space. So all the particles are, their structures in space, et cetera, et cetera, et cetera. And so one of the slightly shocking things about the current kind of estimates from our theory is, if you ask all the things that we experience, the electrons, the quarks, all these kinds of things, the experiences we have in the world, what, if we look at this underlying hypergraph and what it's doing, to what extent is it putting its effort into delivering the universe as we experience it? Well, it seems like about 1 part in 10 to the power 120 of the effort put into the evolution of the universe goes into stuff that in a sense we care about. And all but that 1 part in 10 to the 120 is all to do with the knitting together of the structure of space. So basically, most of the activity of the universe has to do with knitting together the structure of space. And this kind of ER equals EPR quantum entanglement thing, it's all kind of connected to the knitting together of the structure of space, knitting together the structure of quantum entanglements. They're all kind of connected together. And yeah, so the answer is, and in terms of the formal connection between our stuff and ER equals EPR, some people have been working on that, and it's rather beautiful actually. The whole ADS CFT correspondence, which is one of the kind of achievements of mathematical physics over the last 20 years, 25 years, seems like it is a story of different projections of this multi-way causal graph into physical space and into branch hill space and so on. It's a great example of where this sort of low-level machine code that we have provides kind of an explanation and a justification for something that one's seen in traditional mathematical physics.
Interesting. So just to get into a little bit more detail on how your theory actually works, from what I understand, you have this evolution model over this graph of points, right? So you have some kind of notion of discrete points knitted together with some kind of edges, and then the evolution causes like a structure to emerge from that. And then somehow sort of three-dimensional space as we experience it is just coming out of the topology of how the points end up connected together after the fact?
Well, they don't quite get to topology. Topology requires that you have information. All we have is information about these sort of atoms of space. How is one atom of space connected to other atoms of space? That's all we know. We don't know how, to get topology, you need things like faces. You need to know that these 3 edges are the edges of a triangular face. Oh, we don't have any of that information. So the way that you get sort of emergent structure, emergent spatial structure is a little bit more mathematically elaborate. And the mathematics to really nail this down simply does not exist yet. It's something where essentially what we have to invent, or what I hope other people are going to invent, because it's quite heavy lifting, is, so calculus, as it's practiced, is about things in integer numbers of dimensions. We say, there's univariate calculus, 1 dimension, there's multivariate calculus, multiple dimensions, but it's always, and we always, at the end, when we look at space locally enough, it looks like a little piece of standard flat Euclidean space. Well, what we end up with is these things where that just doesn't happen. The things you get, it's like we have to generalize calculus to fractional dimensional space. And there's a whole elaborate story of generalizing differential geometry and generalizing the whole hierarchy of mathematical ideas to what is really, in effect, a fractional dimensional space that emerges from the limits of these hypergraphs. And it is mathematically really heavy lifting. And as is pretty typical in these things, in what we've been able to do so far, and it's what physicists always get a bad reputation with mathematicians for doing, we just bash through all these mathematical issues. And there are all kinds of, like I think in getting to some of the more elaborate things we have to do, we have to take like a dozen limits of, the size of this thing is large compared to the elementary length, small compared to the size of the universe, large compared to the distance, the average curvature of this, et cetera, et cetera, et cetera. Now, in the end, it probably doesn't matter, because if you have 10 to the 400 things, knowing in detail how the limit works doesn't really matter, because 10 to the 400 is a really big number. But when you're trying to do the formal mathematics of it, you can say, well, how do we know that this limit commutes with that limit, and how does this work? And those are really good mathematical questions. But you know, what we're doing is we're kind of a little bit, you know, we're figuring things out, and the fact that we can do computer experiments is kind of critical, because, you know, what we might wonder, is this mathematical theorem true? We can just do an experiment and find out a bunch of sort of empirical evidence for what's going on. And it's kind of a future work to kind of tie down. And by the way, when we talk about tying things down, I mean, for example, the second law of thermodynamics, a fundamental thing discovered 140 years ago or something now, the tying down of its mathematics hasn't yet happened, even though it is absolutely assumed throughout physics. So, you know, this process of mathematically tying things down isn't a process necessarily required to make sort of forward progress on the physics of things. But in any case, you're asking, I mean, the problem is the full stack. So this is one of the difficult things, is that the sort of full stack of explaining how different parts of physics arise from these models of ours, I think I am down to being able to do it in about 45 minutes with a reasonably technical audience.
Yeah. So asks a related question to what you mentioned here. Like, would you describe the computational approach as brute forcing science in terms of, you know, its application to the material world and some of these topics we're discussing?
Not really the way that we're using it here. I mean, that is, there is a sense, I mean, it's complicated because the kind of use of computation in this paradigm, okay, so when you do computer experiments, yes, there's a fair amount of brute force involved there. That is, you do an experiment, just like when you do an experiment in the physical world, you just run something and see what happens. And in a sense, you don't have to know what's going to happen. In fact, to do a good experiment, you need to not make assumptions about what's going to happen when you do the experiment. If you make assumptions, you're likely to get the wrong answer. So in that sense, it is brute forcing in the same sense that doing physical experiments is brute forcing science. That is, instead of figuring stuff out, you're just going and finding out what's true by just, in the case of computer experiments, running programs. In the case of physical world, you know, doing things with test tubes and measuring devices and things like that. Now, there are other aspects of this where one is doing searches, where one's saying something which one can't as readily do in the physical world, where one's saying, I think there's a rule roughly like this that might do this. Let me go search 1 trillion cases and find out whether any of them do it. In that sense, one is doing a certain amount of brute forcing. One of the things I've discovered is that whenever you think, oh, I know how this is going to work, I know where to go look for that rule that's going to do this particular thing, and you go searching in this one particular place, you more often than not get the wrong answer. If you just say, I'm just going to ignore my prejudices and just go, you know, you could call it the brute force thing, and just go search all these possibilities, that's when you discover really unexpected things. And the real trick is to not ignore the unexpected stuff. And like when I first discovered a bunch of things I've discovered about the computational universe, they were so unexpected. The things that I discovered were so unexpected that for a year or two, I ignored them. I just, you know, I was like, well, I don't know, you know, I guess something must happen, but I kind of didn't think it was important. And, you know, that's again, that's why when you make these sort of discoveries and things, the context of how you're sort of primed to think about things, so that when the surprising discovery kind of drops in your lap, you can actually make sense of it. That's a kind of critical piece to it.
Cool, thank you. We are going to combine a couple of questions here that we've gotten about education. So from Jeremy and John, maybe this will touch on some of the institutional stuff we discussed earlier. So when you look at the way that both physicists are being trained today, and the way that even through elementary and high school, people are being prepared to go into scientific fields, how do you think people can be trained better? Do you think the quality of education, these things, has fallen, especially in universities? And, you know, maybe as a tail end to that, are there prospects for computational methods being integrated more into K-12 education?
Oh, there's a lot to talk about there, but I'll say a couple of things.
Give it broad, wherever you'd like to take this question.
I mean, so I mean, I think the main thing is, do people learn that they can discover things? Because most of education isn't, and for many professions that people go into, discovering things is not the point. But if you're going to train people who are going to do sort of innovative science and so on, the most important thing is that they learn that they can discover things and that they learn strategies for figuring out what's worth investigating and so on. And that's absolutely not what's taught. What's taught is the mechanics of how to do stuff, not the strategy of what to do or the idea of how you sort of discover something that hasn't been discovered before. I think one of the things that's really neat about computation is because it is a new paradigm, it's a vast, it opens up sort of vast arenas of possibilities. And it means that the distance, for a person just starting out, how do they get to a frontier? How do they get to the point where they can do things that people have never done before? Well, in sort of computational X, it's actually rather easy in almost any direction to get to the frontier. Once you know sort of basic computational ideas, I admit that the technology stack that I just spent the last third of a century building, I think is pretty useful for being able to do this. It's, that you can kind of write a Wolfram language program, you can kind of, that lets you explore something that it's exceptionally likely nobody has ever explored before. In other words, you can, we do this, like we just finished a thing we do every year, which is a high school summer camp, okay? Where we get, 40, 45 students or whatever it is, doing sort of original projects. And it's amazing how well that works. It's like, you would think, gosh, how can you get high school students to do sort of original projects that are researchy type things that have never been done before? Well, the answer is there's a secret weapon, which is let them use computation and let them use the kind of technology stack we built, because it's a new platform that lets people sort of see further than has been seen before. So I think that's in terms of what's possible in education, I think giving people the idea that they can do things that have never been done before, that's really important. We now have tools that get you to that frontier much more quickly. I think that a lot of education is wound up with things like assessment and so on, and it's much harder. If the thing you're trying to educate people about is the strategy of picking the right problem to study, I have no idea how you assess that. It's not a very good multiple choice, question answering thing. So that's a few thoughts about that.
We've discussed the notion, I know previously on these salons, of apprenticeship, almost like rather than just going through lecture and learning material, it might almost be more useful to perhaps operate in the kinds of working groups we discussed earlier. And, there's a lot of process knowledge, a lot of skills that cannot be taught in a classroom, strategy of how to think about problems and so on. Like, do you think that there's any possibility of those kinds of educational norms, occurring in the scientific world, especially now with the disruption that we're seeing from COVID and so on?
Well, I mean, the summer school that we've done for the last 18 years is basically like that. Mm-hmm. And it's very successful. And actually, the problem of today is we now have about 30 people who are sort of continuing to work on the physics project, who sort of got launched at our summer school. And we are literally today wondering, okay, so how do we set this up? Because we've basically got, I have friends who are professors and they're like, oh my gosh, I've got 4 graduate students and it's killing me. How am I going to deal with that many graduate students? And I realized we've just got 30 graduate students. What are we going to do? How are we going to build the structure? And then I was realizing, well, I know a certain amount from having, run companies for 40 years. I know a certain amount about how to manage stuff. But now the question is, how do you, this is the problem du jour, actually, of, when you're managing a basic science research project, how do you do that? That is, when we've got, and it's easier if you have a very concrete objective you're trying to reach. anyway, this is the problem I'm actually trying to figure out right now. It's something where, and I think it's it's also, there isn't, the economics are kind of it's sort of messy because at this point this is not a commercial project. It doesn't make money. I'm putting some money into it just because why not? But that's not a long-term sustainable scheme.
Right.
So, there's the question of, do we get public support? As in, do we just have, basically become a member? And, kind of like what you guys do, I think. And it's is that a meaningful way to support a piece of basic science? It's kind of like, in a sense, it's like going back to the very earliest days of universities, where people would, unless they were going into the church or something where they had a specific sort of vocational direction at university, I think a lot of kind of professoring was paid for by people who said, oh yeah, I want to come and listen to that stuff. I'll pay this guy, or I think it was always guy in those days, something to go yak for a while, and I'll give them some pennies or whatever it was to be a student, so to speak. Even though the goal of doing that was really just self-enrichment. It wasn't, oh, I'm going to learn a skill type thing. And so, it's possible that there's a new model, and I'm trying to figure this out right now. It's like, what is the model for doing basic science in today's world? And one model is, I think I was mentioning earlier, I think, when there's a monopoly, it makes sense to do basic science. So like when the US government is sort of the dominant economic force, in a sense, the US government can pay for basic science because if something gets discovered in science, there's a good chance the US is going to benefit from that. If you're a little country somewhere, it's much less obvious. I mean, your reasons for funding basic science usually have more to do with, maintaining a workforce and so on than they do to do with sort of having economic benefit from what gets figured out. So I'm sort of actively interested in this question about, is there a new model for how to, it could be that figuring out the fundamental theory of physics probably isn't that expensive. So we don't, at some level, we don't have to, we don't, actually the most bizarre thing, which I will say here, which is if this turns out to be the case, this will be the most bizarre, crazy, you couldn't have made this up type situation. But it seems like one of the consequences of fundamental theory of physics is it gives us a way to think about distributed computation. And there's an application of that, which is to essentially a vastly distributed version of something like blockchain. And so the most bizarre thing that, I say, you couldn't make this stuff up, is that we end up basically building, a distributed sort of transactional blockchain kind of thing that essentially works where sort of essentially quantum, one example is, your balance of money has some quantum uncertainty associated with it, where quantum uncertainty is in a formal sense of these models. So the craziest thing will be that if it turns out that, the development of the theory of physics is kind of financed by the fact that physics allows you to create a distributed blockchain that then becomes, I don't know, an ICO or some generalization of an ICO or something. That will be you just can't make this stuff up.
That's definitely
energy.
That would be a very unique outcome. I mean, coming back to the question of how you fund these endeavors, this is related, we were talking about this earlier with the question of what's your niche, right? What's the niche at the beginning for fundamental science or fundamental thinking? And I mean, we think about this issue a lot as well, because our project is in many ways sort of this intellectual project, right? We're trying to figure out a bunch of these questions. And, well, if you find a solution to it, we'd definitely love to know.
Yeah, I mean, I think this is the challenge of what is intellectual work worth and to whom?
Right.
And at different times in the history of civilization, there have been different models of whether it's, and there's been different levels of interest in, I don't think there's ever, there are these moments, and I've been fortunate to be sort of a beneficiary of one of these moments where sort of the world of intellectual ideas collides with practicality. And that's happened in the practical thinking about computation, computational language, things like that. That's a place, you know, the things that I think about designing computational languages, the things I do there, I have sort of a matrix in which some idea, some pretty intellectually basic idea that I come up with, it immediately turns into, there's this pipeline where it turns into a product and where people can actually use it. And that's, you know, there are these moments in intellectual history where there's been sort of this intersection between sort of the practical and the intellectual. I mean, I think we see that, I don't know, you know, it'll be interesting to see, you know, when AI ethics develops more, will there suddenly be a big market for all these people who understand the philosophy of ethics, so to speak? You know, it's a you know, there are these moments when there's sort of a collision between these things. And in the case of fundamental physics, I'm not really seeing right now that, you know, it's like fundamental physics is interesting, but it's like, you know, and it's also, and, you know, for example, a good example of the sort of collision of fundamental physics with other things was the Manhattan Project that we mentioned earlier. Was like, who cares what, you know, how the nucleus works? And, you know, that was cool, but nobody, you know, in a sense, you might not care. And then there was this, you know, sort of huge application for it. I think, unfortunately, I think that the sort of scale of the physics that we're now doing does not favor that type of, you know, in other words, we might say, yes, we can imagine how to make, you know, warp drive for a starship, but sorry, you need to have a collection of 10 black holes to do that. We don't have, you know, we just don't have those available, so to speak.
Yeah, well, this is a good place to wrap up, I think. We're out of time. Dr. Wolfram, please, very much thanks for joining us. This was a very interesting discussion. We loved talking about this stuff. Definitely learned a lot. For the audience, you can find Stephen's latest work at stephenwolfram.com. Special thanks for all of our Palladium members and audience for the great questions. To become a member and get invited to our upcoming salons, please visit us at palladiummag.com/subscribe. And remember to subscribe to Palladium Magazine on YouTube and follow us on Twitter at Palladium Mag. With that, thanks everyone. We'll see you next time.
Thanks, guys.
Good stuff.